Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 29. We're moving into chapter 9, part 1. We're going to talk about some hypothesis testing. So, multiple regression. Last time we talked about multiple regression. In fact, we talked about the ANOVA table and some examples. And I even talked about the hypothesis test that we were making there. But this time we're going to talk about our test for overall regression. We're going to talk about, in this chapter, something called a partial F-test, a multiple partial F-test, strategies for using these, and some additional inferential methods for multiple regression. This is going to be a little technical, and it's going to take some thinking and keeping things straight and clear. So let's get started. So let's talk about a preview for this section, or this chapter. So after we fit the multiple regression, we'll want to test how much contribution the independent variables give to the prediction of y, or provide, how much prediction power, if you will, if you think of it that way, that the better word is contribution, prediction contribution they provide in predicting y. And so some of the tests we want, our overall test, is the entire model significant as far as trying to predict y? Is it statistically significant? And then we want to test for, should we add another variable? Is it significantly better to add a variable in the prediction of y or not? And so there's the added an order test and the added last test. Okay? And we want to test for the addition of a group of variables. We may ask if the addition of a group of variables contributes significantly to the prediction of y, whether or not or when other independent variables are already present in the model. In other words, we're going to say these variables belong in the model now. Should we add this other group of variables to the model or not? Okay. So each of these tests can be expressed as an F-test. And we talked a little bit about the F statistic last time, but we're going to talk a little bit more. And an F-test can be expressed as a t-test in some cases. So for the straight line model, where we had 1 degree of freedom in the numerator, and we had, say, nu in the denominator, well, t with nu degrees of freedom squared is an F statistic. I hope I got that right. I think I did. All right. So when we have two ratios of variances, and these are chi-squared random variables, if they are independent, then these form an F statistic, all right? And we have an F table, and we're going to go into that F table a little bit. And the term sigma naught squared, that's an estimate of sigma squared. And that's true if H naught is true, right? So we're going to say H naught sigma squared equals sigma naught squared hat, all right, in this case. And it estimates whether it's true or not. Okay, so if it's true, then this term estimates sigma squared. If H naught, whether or not H naught is true, sigma hat squared estimates sigma squared. All right. The rationale of the F test is that when H naught is not true, this estimates something larger than sigma squared. It includes something more than the variance, the actual variance. And it makes the corresponding F statistic larger. So we reject H naught, which means that we should include that variable in the model, or we should include that model, or that model is significant in predicting y. Okay. And so we reject H naught when the F statistic is larger than the critical value. So when F from the table is greater than F critical value, we reject H naught. Oops. Okay. So each test can be interpreted as a comparison of two models, okay? And let's consider this. So we have model 1 that has x1 and x2. And then model 2 only has x1 in it. Now we're keeping the intercepts, and of course the error is a random error. Okay, so we're not changing that notation. And so we can compare those. We can also compare this to y equals beta naught plus epsilon. And that's called a global test, and we'll talk about that as well. Okay, so under H naught beta 2 equals 0, the full model reduces the model 1, okay? So if beta 2 is equal to 0, then basically we get rid of this term. Let me clean this up a little bit. So if beta 2 is 0, then if that's 0, then we basically end up with model 2. Okay, so a test of beta 2 equals to 0 is equivalent to deciding which of these two models is the most appropriate. Okay, and the set of independent variables in the reduced model is a subset of the independent variables in the full model. You can think of it that way. And this way of thinking is important, okay, because we're going to do some tests for this and many of these tests. So it's very important that you understand this. So let's consider this multiple regression model that has k variables, independent variables in it. And here's the test that we want for significance, that all of these are equal to 0, that all of the betas are equal to 0. This is the null hypothesis for the global. This is a global, another word for it is a global hypothesis. And this is testing the overall significance of the model. So if all of these are 0, then that would be that y would reduce to what I said before, beta naught plus epsilon, a constant plus random variation. So another way of saying this is, here's one way of saying it. All k independent variables considered together do not explain a significant amount of the variation in y. Here's number 2. There is no significant overall regression using all k independent variables in the model. Okay? So that's the equivalent to stating the null hypothesis. Two different ways we can say that. So the alternative hypothesis is that at least one beta I is not equal to 0. So HA is often written beta I not equal to 0 for at least one I. This is the best way to write that, or one of the best ways. To perform the test, we use the mean square in ANOVA table. So we use the mean square regression divided by the mean square error. And if you remember from the ANOVA table last time, that's the SSR divided by its degrees of freedom, which is k, and the SSE divided by its degrees of freedom. And SSR is given by y hat. It's the sum of the squares of the difference between y hat and y bar. This is the regression line and the mean. And SSE is the difference in the actual values to the observed values to the regression line. And so the textbook uses regression MS for MSR and residual MS for MSE. And both of these are, so this is equivalent to MSR or MSM sometimes for model, okay? And so residual MS is MSE as well. So various names, but most of us like to use MSE or SSE. So you won't be confused if you take Stat 400, use the same kind of notation. All right. Under H naught, the F statistic follows an F distribution with k degrees of freedom in the numerator, n minus k minus 1 in the denominator, and the critical point of the test would be here, where we have f with k, n minus k, 1 minus alpha. Not alpha over 2, but 1 minus alpha, even though our alternative is not 0. Okay? So if our statistic, as we said, is larger than that critical value, then we reject H naught. And we can show that the F statistic can be expressed in terms of R squared. So here we have R squared over K, 1 minus R squared over N minus K minus 1, okay? So we're not going to go through the derivation, but let's do an example. So this example comes from section 8.7 with the regression of WGT weight on height, age, and age squared, okay? So we have N equals 12, K equals 3, MSR is here, MSE is here, and R squared is here. So we can calculate this using MSR, 231, divided by MSE, but we can also use it with R squared divided by K and 1 minus R squared over the degrees of freedom of the error. And the critical point is F3 and 0.99, 1 minus alpha. So let's find this in the F table. So it's 0.99. We look at the F table, and it's strange to me that they have highlighted this area over here to the left of the critical value, but this says upper 25%, so that would mean that upper is 0.25 up here, so this would be 0.75. So I guess they've highlighted this because this 0.75 is what we're, what we would be looking for in the value. We don't want 0.75, we want 0.99. So to get 0.99, we have another page with 10%, upper 10%, or 0.9. And so we keep going. And now we're at 5%, so 0.95. And then we keep going, and we get to 0.975. And we keep going, and now we're at 0.99 because the upper 1%. So that would be F of, let's see, what do they use? Do they tell? No. Numerator, let's say V1, nu1, nu2, and then 0.99. So we were looking for, I believe, let's see, I don't want to say, I don't remember. We were looking for 3 and 8 degrees of freedom here. 3 in the numerator, 8 in the denominator. So the numerator, you have to look, is here. So we want 3, and then we want the denominator is over here, and we want 8. So 8 is here, and we come across, and here is, I'll zoom in, 7.59. And you'll see that that is the value that they have, 7.59. And so since F equals 9.47 is greater than F critical value, which is 38.99, which is equal to 7.59. Since this is true, we reject H naught. Okay? So based on the data, these variables are significant in predicting the weight. But this doesn't mean that all three variables are significant. It means that together they're significant, but we need to look at each one individually to see if they are significant, and we will do that in a future video. So don't forget to scan your lecture notes by midnight, the date listed in the course calendar. If you have any questions, come to virtual office hours. If you can't, email me, but email me a picture and the problem itself so that I know how to help you. And I hope you'll take care, and we'll see you next time.